All right, we'll go ahead and get started. We're going to pick the lecture up where we ended off last time, and we were talking about diffusion in polymers and how it's often described in terms of an activated state process modeled by an Arrhenius equation. And within the context of this model, one can apply the transition state theory to give an expression for the frequency of diffusion steps in terms of the Gibbs free energy between the activated and ground state. And we remember that we think about an activated state as one in which polymer chain segmental motion has brought about a gap in the polymer matrix through which a penetrant can diffuse. From thermodynamics, this activation free energy can be written in terms of the activation enthalpy and the activation entropy, and it turns out that those two terms are related to one another, as we'll see here in just a moment. We can combine this definition together with the fact that the diffusion coefficient depends upon the square of the jump distance times the frequency of jumps, and this is the expression for the frequency of jumps that comes out of activated state theory, to get the expression for the diffusion coefficient shown here in the middle of slide 9, where we start to see the appearance of the entropy change associated with going from the ground state to the activated state. Historically, the enthalpy change associated with going from the activated to non-activated state is written in terms of the activation energy of diffusion and RT. Combining these results gives the expression in the middle of the page, and when we compare that back to the original Arrhenius expression for the diffusion coefficient, we see that this front factor, which we call D0, is related to the activation entropy, that is the entropy change between the activated state and the ground state or unactivated state. And we'll see what that means physically a bit more in just a moment. It turns out that the two parameters that appear in the activated state theory, that is this front factor D0 and the activation energy ED, are not independent of one another. And in fact, Barer and Van Amerongen found that there was a linear relationship between activation energy of diffusion and the logarithm of that front factor, that is, between the logarithm of D0 and ED, that there's a straight line relationship between those two. The parameter A was found to be independent of polymer type. It has a universal value of 0.64, and B was found to depend only on whether the polymer was flexible and rubbery or whether it was glassy, and so there were two different values for B. The data that underpin that are shown here, and you can see that for a wide variety of different small molecules in rubbery polymers, for example, all of the data line up more or less around this single line. And likewise for the glassy polymers, you see some scatter, but more or less there's a very strong correlation between this front factor and the activation energy of diffusion. This relationship is so ubiquitous throughout transport phenomena that it has a special name. It's called a linear free energy relation, and that is a relationship between the activated state energy and the logarithm of the front factor. You'll remember that the logarithm of this front factor, D0, is proportional to the entropy change between the activated and unactivated states. We're going to talk just a bit more about what that means here in a moment. But the logarithm of D0 is proportional to delta S star. ED, on the other hand, is directly proportional to the delta H of the activated state. So these thermodynamic parameters, that is the delta H and delta S associated with reaching the activated state are highly correlated. That's what this result indicates. Essentially, what it means is that the stronger the temperature dependence is of the diffusion coefficient, that is, the greater ED is, the greater is the activation energy, and the lower is the diffusion coefficient. A practical use for this is to combine the expression for the diffusion coefficient based on activated state theory with this empirical linear free energy relation, and you get the expression shown here at the bottom of the page. A and B will be known parameters for a given family of polymers. And what it says is that if I measure the diffusion coefficient of one penetrant at a single temperature, I could then calculate the activation energy of diffusion, because A and B are known from these studies from Van Amerongen. If I know that the polymer is rubbery, for example, B is 9.2, A is always 0.64 in both glassy and rubbery polymers. And so by measuring one diffusion coefficient and using this correlation, I can calculate ED and then be able to calculate diffusion coefficients at any other temperature I would desire. And so this is a good way of estimating diffusion coefficients if no other data are available. The next step in this is to ask what's the fundamental basis for this linear free energy relation. And it turns out that throughout transport phenomena with processes that obey activated state, exhibit activated state behavior, one often finds a linear free energy relation. It's really quite remarkable. So if we look first on the right-hand side, this is plotting, if one were to write the viscosity of liquids as eta for the viscosity is equal to eta naught e to the minus E sub eta over RT, where E sub eta is the activation energy for viscous flow, and eta 0 is the front factor for that Arrhenius expression, that there's an extraordinarily strong correlation between 1 over the front factor and the activation energy for viscous flow. Look at the way the data line up on this plot. The temperature range that is spanned by the data here go from 90 Kelvin up to 1,000 degrees Kelvin, and it encompasses everything from nonpolar and polar liquids all the way up to liquid metals and ionic melts, that is molten salt. And so we find in this case that the front factor on the viscosity equation, or 1 over that front factor, is highly correlated with the activation energy of viscous flow in just a wide variety of materials over a very wide temperature span. It's most remarkable. Similarly, one can measure the rates of a chemical reaction, and the rate of reaction will be equal to a front factor times E to the minus activation energy over RT. It turns out that the activation energy in that rate equation is very strongly correlated with the logarithm of the front factor. You'll remember just a few slides back that the logarithm of that front factor in the activated state theory for diffusion, reaction kinetics, or viscous flow, the logarithm of that front factor is proportional to the entropy change associated with that, in this case, reaction. And what's remarkable here is that for a variety of compounds, that there is a very strong relationship between the logarithm of the front factor, or the entropy change associated with the chemical reaction, and the actual activation energy. What's observed in this case is that there is one general correlation line for meta and para-substituted benzoyl peroxides, and another for ortho-substituted benzoyl peroxides. And it's argued in the literature that this separation indicates that the mechanism for this chemical reaction is somewhat different in the ortho-substituted case than it is in the meta and para-substituted case, which one might easily imagine given the changes in steric hindrance and other factors that are associated with this change. So across transport phenomena, we see these linear free energy relationships are not strictly related or restricted to diffusion. And so there's been a significant amount of effort in the literature to try to understand the molecular basis of such linear free energy relationships. And there are basically two competing hypotheses. One is that the observation of a relationship between D0 and ED is simply a mathematical artifact. That is, it's a compensation effect. So if you can imagine that one would plot, for example, one would measure diffusion coefficients as a function of temperature, say for a small molecule in a polymer, and then plot the logarithm of those diffusion coefficients against 1 upon T, and take the slope of the resulting line to be the activation energy of diffusion, and extrapolate to 1 over T is equal to 0, that is to infinite temperature, to get the value of D0 in the activated state expression for diffusion coefficients. If there were some uncertainty in the experimental diffusion coefficients that tilted that line among the data points just a little bit up, for example, that would tend to give it a steeper activation or larger activation energy of diffusion, making the line steeper, and that would also give it a higher value of D0. If, on the other hand, there was uncertainty in the data that tended to tilt that line a little bit down, it would make the the apparent activation energy of diffusion lower, and it would reduce the value of D0. And so this comes about because, in fact, if you look at the range of absolute temperature over which we normally probe diffusion phenomena in polymers, we typically span a very small range of 1 over absolute temperature. And so the diffusion coefficient range that we often probe as a function of temperature is not that great, and any uncertainty in that can then cause this tilting of the line that's fitting the diffusion coefficient data versus 1 over T, and give rise to highly correlated behavior between the front factor D0 and the activation energy ED. Another hypothesis is that the existence of these types of linear free energy relationship is suggesting that the diffusion mechanism among many polymers is similar. And the argument here goes along the lines of another feature of transition state theory, and that is that the log of D0 is proportional to the entropy change of activation, and the size of that activated state or activation zone, or so-called activation volume, determines both the activation energy, ED, as well as the activation entropy. And in fact, there's a model by Lawson and Keyes that puts this into practice, and it asserts that the activation entropy of activation is proportional to the volume of activation, that is the change in local volume around a penetrant that occurs when the polymer chains reach the activated state to allow diffusion to occur. Parameters alpha and beta are expansion and compressibility coefficients. You can find more details about that in the paper papers by Lawson and Keyes. And they relate also this activation volume directly to the activation energy of diffusion, and so the activation volume connects then the activation energy of diffusion with the entropy of activation. And in the context of this model, one should expect that the activation entropy and activation energy are correlated, and that would lead directly to the linear free energy relation shown here, because the log of D0 is proportional to the volume, or is proportional to the entropy of activation. Another way to view this from a practical point of view, or a simple point of view, is to imagine that as a penetrant is making its way through a polymer, it sees an energy landscape that it must traverse in order to make a diffusion step. That is, it has to gain sufficient energy to cross a barrier to diffusion. This would correspond to an opening in the polymer segments that creates a gap through which the penetrant can move from one state to another. And if that energy landscape tends to look like this, more like rolling hills that have broad shoulders and wells that are not too deep, the depth of this well is proportional to the activation energy of diffusion, and the width of the well can be shown to be proportional to the entropy of activation, and a wide width of this valley gives the penetrant more degrees of freedom to move about in this space with no energy or little energy penalty, and that leads to a high value of delta S star. So again, the height of this barrier is ED, and the width is proportional to delta S star. And if one has an energy landscape that would tend to have a low ED, it also tends to have a broad trough, and that gives corresponding values of delta S star. On the other hand, in a situation where the energy barriers are really high in a material, these energy barriers tend to be separated by regions that are narrow, and as a result, then high levels of activation energy, that is the energy required to go from the bottom of this well to the top of this energy landscape to get into the next energy well. As this value goes up, then the delta S star, the activation entropy, tends to be smaller, and that then gives rise to the correlations we've been talking about. A lot of this is borne out by molecular simulations on polymers now, but this particular topic, that is the definition of this linear free energy relation, is still one that is not completely ironed out in the literature. And it might seem intuitively obvious that diffusion coefficients decrease as the size of the penetrant increases, and that in fact is true. It might be somewhat more surprising that even today we don't know exactly how to write quantitative predictions of how diffusion coefficients will change with penetrant size, and in fact don't even know exactly the best measure of penetrant size to use to capture the effect of size on diffusion coefficients. And I'll explain why that is here as we go on in the next few slides. But one example of a correlation of diffusion coefficients with penetrant size is shown here. This is from a book chapter by Richard Baker and Hans Wymans, and it plots diffusion coefficients of a variety of penetrants in a rubbery polymer, natural rubber. So this is the material, for example, that would be in automobile tires, and the material that would be in the little balloons that you might that you would see that you could get to blow up for birthday parties and things of that nature. What you can see is that the diffusion coefficients in natural rubber decrease as the size of the molecule increases, and they kind of level off in large molecules out here like butane and pentane. In polyvinyl chloride, which is a glassy polymer at room temperature, this would be the material that you would know because the plastic water pipes that are ubiquitous in homes and businesses are made out of polyvinyl chloride. And so this is a rigid plastic material. And here you can see that diffusion coefficients vary over many orders of magnitude, almost 10 orders of magnitude, 9 orders of magnitude. So a factor of a billion decrease in diffusion coefficients as you go from helium up to hexane. And so you can imagine that if you were trying to separate some of these penetrants based on size, that a material like polyvinyl chloride would be much more effective at that as a separation membrane, for example, than would natural rubber. Plotting the data against the van der Waals molar volume, one of the things that we're going to see over the next few slides is that there is no universally agreed upon measure of penetrant size that always that's predominantly used to scale diffusion coefficients in across the field of transport phenomena in polymers. The van der Waals volume is one measure of penetrant size that would be widely reported, but it's not the only measure that's useful. We'll see the values like the Lennard-Jones diameter of a penetrant is another value that's often used to scale diffusion coefficients and related parameters. So this will be just the Lennard-Jones diameter out of the Lennard-Jones potential model for intermolecular potentials squared. And in this case, a correlation is noted between the B parameter in free volume theory and the size, or the size squared, of the penetrant molecule. We'll describe in a moment why we're plotting the data in this case versus the square of the diameter. If you recall from free volume theory, FFV is typically estimated, or often estimated, from the density of a polymer. In this case, these are polyethylene oxide cross-linked hydrogels. So the fractional free volume is estimated from the density of these materials, corrected for the volume in the sample that is occupied by the atoms and is not available for molecular transport. And a higher value of B indicates that the diffusion coefficients are more strongly sensitive to free volume. So very small penetrants have small B values, and their diffusion coefficients, if you look at a series of these materials, their diffusion coefficients change relatively little with free volume, or are relatively insensitive to free volume, whereas large penetrants like ethane are very sensitive to even small changes in free volume. And it turns out that this comes about as a result of the fact that if you think about how to open gaps in a polymer matrix via thermal motion that would allow diffusion steps to occur, it requires very little energy to open a small gap in a polymer matrix. And so Small gaps are created very frequently in polymers due to the thermal motion of the polymer chain segments. And so there are always, or are very frequently, free volume elements of a size that can accommodate helium and hydrogen. To open a gap large enough to accommodate a much larger molecule like ethane is a much rarer phenomenon. It requires a larger fluctuation in chain motion inside the material to create such a large gap, and that requires a lot of energy, and these highly energetic transitions occur very infrequently. That's another byproduct of the transition state theory that we're just talking about. And so within the context of the free volume model, higher values of B are generally associated with larger, in a given polymer, are generally associated with larger penetrants that require more volume to open up in order to make a diffusion step. Or alternatively, such molecules are much more sensitive to the free volume and slight changes in free volume than would be small molecules that can get through most any free volume element that might open up. Another factor that influences diffusion coefficients is not only the size of a penetrant but also its shape. And that's shown here for the case of CO2 and methane transporting in bisphenol A polysulfone, which is a membrane that's widely used for gas separation. It has a TG of about 186 C, so at ambient conditions it's a rigid, glassy polymer. Here are the permeability, solubilities, and diffusion coefficients of carbon dioxide and methane in this material. And you might think, before having a close look at the subject, it might be tempting to say, okay, well, if diffusion coefficients go down as the size of the penetrants go up, perhaps one factor that would scale diffusion coefficients would be the molecular weight of the penetrant. That is, molecules with higher molecular weights would be in some sense larger than those with lower molecular weights, and therefore penetrants with higher molecular weight would diffuse more slowly than those of lower molecular weight. And so if you look at CO2, it has a molecular weight of 44 grams per mole. Methane is 16 grams per mole, and so on that basis, one would argue that methane should have a higher diffusion coefficient than carbon dioxide. There's no polymer that I'm aware of that obeys that trend. So in all polymers, CO2 is always more mobile or has a higher diffusion coefficient than methane. In the case of polysulfone, that ratio is on the order of almost 6, so 5.6. So CO2 diffuses 5.6 times faster than methane in this material. And the argument is that methane is a spherical molecule and has an effective diameter or kinetic diameter of 3.8 angstroms. CO2, however, is not spherical. It's more of a football-shaped or elongated molecule, and its narrow dimension is about 3.3 angstroms, actually about half an angstrom smaller than the diameter of methane. And so you can imagine in a polymer where thermal fluctuations are bringing about fluctuations in free volume elements, and that these gaps or free volume elements that have low volume require little energy to be created, and therefore they occur very frequently. And so if penetrant molecules are vibrating around inside free volume elements in polymers waiting for local scale molecular motion to randomly open a gap next to them so that they can take a diffusion step, the probability of having a small gap open next to a penetrant due to thermal diffusion or thermal molecular motions of the polymer chain segments, the probability of having a small gap open up is much higher than that of having a large gap open up. And so CO2, which could diffuse in any dimension that was available to it, will find more opportunities to execute diffusion steps if it can squeeze through in this elongated state or through its narrow direction. And so what's found with asymmetric shaped penetrants is that they execute successful diffusion steps more often if they're moving in the direction of their narrowest cross section. And that's just simply a reflection of the fact that if they're trying to go through a polymer sideways, that is, based on their long or large dimension, that the number of opportunities to do that, the frequency of appearance of such gaps that are so large is much smaller than the frequency of appearance of gaps that correspond to the narrow dimension of a penetrant. You can imagine if you were trying to get through a hole or a tunnel that's 2 feet wide, you're not going to go very far if you try to go through upright, but if you go through in your narrow dimension, you could easily go through a tube of that size. And so that's essentially what's happening with the penetrants. They tend to diffuse in the direction of their narrowest cross section or narrowest cross sectional area. Patrick Mears in the UK proposed a mathematical model that embodied many of the features that I've been talking about over the last few slides and put them down in equation form. And the so-called Mears model is based on a very highly simplified picture of the creation of an activated state for diffusion, activated volume of diffusion, and it presumed that the activation energy of diffusion was equal to the volume of the activated state times the polymer cohesive energy density. Avogadro's number is in here just to balance the units on it. Well, let's think about what this means for a moment. If one imagine that when polymer chains separate to create a gap through which diffusion can occur, that gap is almost certainly not cylindrically shaped, but it is elongated. They would tend to be perhaps longer than they are wide, and so Mears approximated that activated state volume as a cylinder of diameter d sub a and of length, the jump length L sub d. And so the volume of this cylinder is given by pi by 4 L sub d times dA squared. And Mears reasoned that in order to create a volume of this size, that is pi by 4 LD times dA squared, it required overcoming the cohesive interactions between the polymer chains, which were characterized by the polymer cohesive energy density. This is what we've seen earlier when we talked about solubility of polymers in solvents. We saw the polymer solubility parameter, and the square of the solubility parameter is the polymer cohesive energy density. It is the strength of interactions that act to encourage polymer segments to stick to one another. And the higher is the cohesive energy density, the stronger is the interaction of polymer segments with one another. And so Mears's model said that the activation energy diffusion depended upon the size, the volume of the activated state, and the polymer cohesive energy density. And so polymers with higher cohesive energy density, that is those with favorable interactions, hydrogen bonding, this sort of thing, could be expected, all other factors being equal, to have higher activation energies for diffusion, because you have to put in more work to create that volume for the penetrants to go through. On the other hand, penetrants that have high diffusion coefficients, that is, require a large value of D sub A in order to execute a diffusion step, are also going to have very high activation energies. And so we'll show a couple examples now of the use of Mears's model. There's a bit more writing here that I'm not going to go over in depth, but I'll leave that for you to summarize a bit more of Mears's work. But here's an example from Mears's original paper, where the square of the penetrant diameter or cross section is being correlated with the activation energy of diffusion in polyvinyl acetate, and Mears used data like this to help support the model that he had proposed on the previous page. There are also reasonable correlations with the cohesive energy of the polymer. I'll show that here in just a moment. One of the criticisms of the Mears model is that, if you look back a couple slides, this is really an incredibly oversimplified view of what could be a very complex phenomena in a real material. And one of the things that this model doesn't get right is it predicts jump lengths that are really long. And so one case that Mears had put together for a copolymer of polyvinyl acetate and PVC had jump lengths of the order of 84 angstroms, and this would be many times the few angstrom jump length that most people would associate with this sort of phenomena. Another implication is that not all of the volume involved in the activation state would be accessible to the penetrant. That is, that this activated state volume might be a long and narrow region, and that a lot of energy might go into activating portions of that activated volume that were simply too small to hold the penetrant. At least that was some of the arguments that were advanced for this. One of the pieces of evidence presented for this is correlating the apparent activation volume calculated from the Mears model. That is, this would be the apparent activation volume, correlating that with basically the volume of the penetrants, and you can see that the volume that the penetrants might occupy is way smaller than the activation volume that's calculated from the Mears model. That is from this value, and that led Mears and others to postulate that the energy and the activation energy was being used to spread apart polymer chains in regions that were not very large, and in regions that were many regions that were penetrant inaccessible. Another feature of this model is that it predicts that the activation energy would go up as the cohesive energy density of the polymer went up. And an example of that qualitatively is shown here for a series of rubbers that are made from polymerizing these monomers. And the cohesive energy density of these monomers goes up in this order. These are low molar mass monomers that are polymerized to form polymers, and so these monomers actually can boil as liquids, and their boiling point also goes up over this same range. So the higher the boiling point is, the greater is the cohesive energy density between the monomers. The higher is the cohesive energy density in the monomers, the greater is the cohesive energy density in the polymers once they're made. And in polymers with higher cohesive energy density, the activation energy of diffusion is higher. At least that's qualitatively what's being argued by this model. Now, even with these shortcomings, the Mears model, at least qualitatively, does provide useful insights for diffusion in polymers. Because ED appears in the activated state theory in the exponential term, that is D is D0 e to the minus ED divided by RT, what this result means is that the logarithm of the diffusion coefficient is often proportional to the negative of the square of the penetrant size. And so what you'll find in many cases in the literature are correlations either where the log of the diffusion coefficient goes down steeply with some measure of the penetrant size or penetrant size squared, or activation energy data are plotted versus some measure of the square of the penetrant size. And so that this shows one correlation of data for a variety of polymers, and shows the activation energy scaling for a variety of penetrants in different polymers, scaling with the square of the molecular diameter, here just being the Lennard-Jones diameter of the penetrant squared. And so another correlation that is has been advanced by Van Amerongen many years ago shows activation energy correlated here with the diameter of the gas molecules. And again, qualitatively, what you can see is that the larger the molecules are, the greater is the activation energy of diffusion, the greater is the amount of energy required to reach the activated state, to open a large gap to let large penetrants through, than for a small molecule like helium. And so that concludes this section of notes. And I will now pass to lecture notes 11. And we'll talk now about, briefly at least, about one additional model. I'm not going to present a lot of information on it, called the Brandt model. And the reason I want to talk about it just a bit is because it captures a notion or an idea in diffusion phenomena that is not captured in the Mears model. So the Mears model is all about the activation energy of diffusion coming from breaking the cohesive bonds between the polymer segments to permit the creation of a gap that would turn out to be the activated state for diffusion. And Brandt had hypothesized also that there were other contributions to the activation energy of diffusion besides just the energy required to separate for example, separate polymer segments from one another to create a gap through which penetrant motion could occur. Brandt argued that indeed there was an intramolecular energy. This is the energy that Mears was talking about, that was needed to bend or separate segments of polymer chains to accommodate the penetrant, and that one depends on the product of the penetrant diameter squared and also the height of the potential energy barrier to polymer segment motion, which Mears took to be proportional to the cohesive energy density of the polymer. Brandt also argued that if you moved apart two polymer segments or moved apart polymer segments around a penetrant to create a volume through which the penetrant could diffuse, that those polymer segments were pressing against their neighbors around them, and there was an intermolecular contribution. Excuse me, I have got this. There was an intermolecular contribution, and that contribution depended on the product of not the diameter squared, but the penetrant diameter and the polymer cohesive energy density, or so-called internal pressure. And so the Brandt model has two terms in it, one proportional to the square of the penetrant molecule and the other proportional to just the penetrant diameter to the first power. In some, there are arguments in some cases that, for example, in rubbery materials like polyethylene, the fusion coefficients are seen to increase linearly with penetrant diameter, and this is taken to indicate that the dominant contribution to the energy of activation is not this first one that that Mears was so concerned about, but it is this second factor that Brandt introduced. In fact, it's really, we're often changing penetrant size over a narrow enough range that we often, empirically at least, can't distinguish between activation energy that depends on the square of the diameter and one that goes linearly with diameter. And so we don't emphasize this model, certainly not in the modern literature very much. And I only bring it up here to remind us that there are likely other contributions, the activation energy of diffusion, than simply the polymer cohesive energy density. The Brandt model has never really caught on in the literature, despite being around for a while. A feature that neither of these two very simple models capture is shown in this plot. And this is showing activation energy of diffusion, now using van der Waals constant as a rough measure of penetrant size. The activation energy of diffusion increasing and then plateauing as you get to large penetrants. That is, over here, as you go through from helium up through the light gases and some of the light hydrocarbons, there's a strong increase in activation energy of diffusion with increasing size of the penetrant as characterized by this van der Waals constant. And then beyond a certain value, the activation energy of diffusion doesn't change very much, even as the penetrants get much larger. And this has led to discussion that in the large penetrants that they may have sufficient flexibility and conformational freedom that they don't diffuse all in one go. So you imagine a small molecule like helium or hydrogen. When one of these H's takes a diffusion step, you can be sure that the other one is right behind. And same thing with oxygen, nitrogen, and CO2. That is, the molecule moves as a single unit, and so it's the size of that single unit that is relevant for how large a gap is required to be formed in the polymer to allow diffusion to occur. As you get out to large enough penetrants, these very large penetrants, like pentane and even larger, are going to start to exhibit many different conformations and the possibility of the molecule diffusing in pieces. by undergoing molecular rotation as it moves through a polymer. And so what's found is that in these larger, more flexible penetrants, the activation of energy of diffusion actually plateaus. It no longer goes up relentlessly with the size of the penetrant. And it's also worth noting that in butyl rubber, at least, where this maximum is located at 70 kilojoules per mole, that is the activation energy for viscous flow. That is, if you measured the viscosity of butyl rubber as a function of this particular butyl rubber as a function of temperature, you would find that its viscosity changed with an activation energy for viscous flow of about 70 kilojoules per mole. And so that prompts the notion that the energy required for diffusion of large penetrants is similar to that required for viscous flow of the polymer segments, which is an interesting concept in the literature. For glassy polymers that have built-in non-equilibrium excess volume, it's often found that activation energy is proportional to the square of the penetrant diameter, and the diameter that is probably most widely used in the literature to characterize penetrant size is the so-called kinetic diameter, which is the smallest rigid pore in a zeolite through which a penetrant molecule can fit. There's the use of kinetic diameter has been very widely popularized in the 80s, 90s, and on through today. Collision diameter based on the Lennard-Jones model is also sometimes used, although fitting unique values to the Lennard-Jones parameter can be challenging, and so the collision diameters that are calculated from, for example, the Lennard-Jones parameter characterizing molecular size often is not a unique value. These kinetic diameters are reported for a lot of small molecules. They're not reported, frankly, for a lot of very large penetrants like drug molecules and things like this that might be of interest. And so, to a first approximation, we can model the effect of penetrant size, for example, based on kinetic diameter on activation energy of diffusion as shown here, with the activation energy of diffusion going as the square of the penetrant diameter. And it turns out that this parameter C is a measure of the polymer chain stiffness, so you can imagine that as C increases, for a given penetrant size, the activation energy increases. So you could attribute this to increasing cohesive energy density, increasing chain stiffness, barriers to creating the gaps to allow a penetrant of a certain size going through. You can also think about a case where in this particular model, where the penetrant size, as it goes down and down and down, perhaps to penetrants that are only hypothetical, that are smaller than any real penetrants, that there would come a penetrant size because of the values of these parameters. F is typically negative. There would come a value of the penetrant diameter where the activation energy would then go to zero, and you could then imagine that particular penetrant diameter, which would be minus F divided by C raised to the 1/2 power, that is the diameter if you set ED equal to 0, that would be some measure of average interchain spacing. And so you can imagine that that polymer segments don't pack perfectly in an amorphous solid state. There are some tiny gaps and regions between them, and if a penetrant were of fractions of an angstrom in size, that it could work its way through that polymer matrix without ever requiring any segmental motion to allow diffusion to occur. And so that's what this value represents. Van Crevelen, which is a real Bible of correlations of polymer properties, reports values of C parameters for diffusion in a wide variety of polymers, and gives ranges of them being around 250 in these units for something that's very flexible, up to about 1100 for glassy polyvinyl chloride, which is a rigid material. In glassy polymers that have rather low values of free volume, F can be about equal to 0, and in really open materials like poly 1-trimethylsilyl propyne, which we talked about in connection with mixed gas sorption and dilation previously, is one of the most permeable polymers known. This F value can be very large, and this quote-unquote interchain spacing can be, by this estimate, on the order of the size of gas molecules. Now, this is an empirical correlation, and so you shouldn't read an absolute molecular interpretation into these parameters. But what it goes to show is that in very open materials, very high free volume glassy materials like PTMSP, there could be a fair amount of space between the polymer chains in the material. So this particular model is used, is often obeyed when one is considering light gas molecules, like the lists that are shown here. You can imagine that this model will fail like the Brandt and Mears models do for very large penetrants like ones out here. It will not predict accurately the dependence of activation energy on effective molecular size. And here's an example of the use of this equation to describe the activation energy in a variety of polymers. It's interesting. One can actually make an estimate of the a model from the previous model of activated state diffusion theory, where we've used the linear free energy model to replace D0 by the A and B parameters. And that can be combined with the model that's shown here that relates ED to the square of the penetrant diameter. And one can derive a model shown here in the middle of slide 8 for the dependence of the diffusion coefficient on the square of the penetrant size. A and B, remember, are essentially universal correlations, and C and F are polymer-dependent parameters. But if you have C and F based upon diffusion coefficients determined for a couple of penetrants, then this gives you a mechanism to predict, at least over a limited range of penetrant size, to predict diffusion coefficients of penetrants that haven't been measured. A problem in this field is which value of gas diameters to use in this correlation. And as indicated earlier, with diffusion being a kinetic phenomenon, the non-spherical molecules diffuse more rapidly in the dimension of their smallest cross section. We showed this slide a bit earlier, showing how CO2, although it has much higher molecular weight than methane, actually diffuses much faster because it's believed to diffuse primarily via diffusion steps in its narrow cross section, which is only about 3.3 angstroms relative to methane, which is about 3.8 angstroms. So kinetic diameter, which captures the narrowest cross-sectional size of molecules, is often used to correlate diffusion coefficients of light gases in polymers. And it doesn't work as well for large molecules for the reasons that the Brandt and Mears model fail for very large molecules. And here on slide 12, I just provide for you a list of kinetic diameters that are reported for a variety of molecules. I also, one problem with kinetic diameter is that it's only reported for a handful of penetrants that might be of interest. I've often found, at least qualitatively, that the critical volume of a penetrant, that is its volume at its critical point, is often also a good scaling factor for diffusion. And in fact, drawing on analogies with diffusion coefficients of small molecules in liquids, one often sees those diffusion coefficients correlated with the critical volume of the penetrant, and with data in polymers. One way to correlate those diffusion coefficients is to plot the log of the diffusion coefficient against the log of the critical volume, and then that plot has a slope of eta and has a front factor of tau. And it's useful in cases where you might not have the critical volume for penetrants where you might not have the kinetic diameter for penetrants where kinetic diameter values are not reported, and for larger penetrants where kinetic diameter simply doesn't give a good measure of penetrant size. One of the outstanding problems in this field would be to really develop estimates of penetrant size from first principles that could be used in diffusion coefficient correlations. We simply don't have that today. So here's an example of this empirical correlation of diffusion coefficients with critical volume in polysulfone and PDMS, and it works pretty well. And one of the things that it shows is that in the glassy material, polysulfone, where diffusion steps are much less frequent and the sizes of the free volume elements that can be readily generated with the thermal energy available, in this case at 35 degrees C, leads to very few opportunities for a large molecule like butane to diffuse, but still something tiny like helium can work its way fairly quickly through that polymer matrix. In silicone rubber, which has polydimethyl siloxane, has a very low glass transition temperature, minus 123 degrees C, and the mobility of the silicone rubber matrix is almost liquid-like. It's an extremely mobile matrix, very little activation energy required to open even large gaps. And so you see on this plot of diffusion coefficient versus penetrant size, in silicone rubber that the data fall on a curve that doesn't have nearly as much slope to it as the polysulfone. And we often refer to a material like polysulfone that has a steep slope on this kind of plot as a strongly size-sieving material, meaning that diffusion coefficients change by a lot as the size of the molecule goes up. Strongly size-sieving polymer. And PDMS, on the other hand, would be an example of a weakly size-sieving polymer. That is, as the size of the penetrants go up, the diffusion coefficients go down, but not by so much. And this is coming about because in PDMS, the barriers, the cohesive energy density between the polymer chains, the barriers to rotation about the polymer segments are so much lower than they are in a glassy material like polysulfone that at ambient conditions, 150 or more degrees above its TG, molecular motions are widespread, and the occurrence of gaps that are large enough for even large molecules like propane and perfluoropropane occur with great frequency, much greater frequency than they do in something very stiff and rigid and glassy like polysulfone. And so the slope of this curve, or this eta value, can give some indication of how strongly these materials sieve penetrance based on size, or how much one could distinguish between transport rates of these penetrants based on the size of the molecule. And that's very useful for applications like gas separation. These are some values of the steepness of that slope eta, going all the way from liquids up to things that are very glassy and very strongly size sieving. So in polymers, those values of that slope go over a range of about a factor of 5 or so, and you can see the value in liquids that's in the textbooks and handbooks on correlations for diffusion coefficients of penetrance in liquids is much smaller than even in silicone rubber. And what that would mean on a plot like this is that if one were to plot on here the diffusion coefficients of these penetrants in a liquid, that there would be an even much shallower slope, or less change from molecule to molecule in the diffusion coefficient of those molecules in a liquid. And that just reflects the fact that unlike polymers, liquids are not all interconnected with one another, and so they can move much more freely, and there's much lower energy required to create a gap that can fit penetrants of many different sizes. And so this section of the notes will actually be actually represents a new topic, and so I'm going to stop the lecture here, and thank you for your time, and I look forward to seeing you next time.